So thank you all for coming today, and it is my pleasure to introduce today's speaker, Nikku Madhusudhan from the University of Cambridge. He is a leading expert in exoplanetary atmospheres and the search for habitable worlds beyond our solar system. He is particularly well known for introducing the concept of Haitian worlds, potentially habitable ocean planets with hydrogen-rich atmospheres, which has opened exciting new directions in exoplanet research. Today, he will speak about recent advances in the search for habitable environments, including new results from the James Webb Space Telescope and their implications for the search for life beyond Earth. So please join me in welcoming Professor Nikku Madhusudhan, and the floor is yours. Thank you.
Thank you. Thanks, Alexandra. You can see my screen fine?
Yes, I can see your screen.
Great, great. So we'll get started. So thanks everyone. A very good morning for coming in early. So uh, we should take one step back and realize where actually we are in astronomy today, in modern astronomy. And to me, it's a quite a profound time we are going through. And as you'll see in this talk, for the first time ever in the history of our species, we are seeing signals of atmospheric signatures of planets that are potentially habitable. Whether these are actually inhabited, in other words, whether they have life or not, is a big question. There is a lot of debate going on, as it should be. But the bigger picture point is that we never even had a chance. We never even came this close ever before. And even today, if you ask about Earth-like planets, we are still not there yet. But the excitement is from the fact that we are seeing any signals at all. And that is huge if you think about it from a technological point of view. So that's the big picture from which I start. And in today's talk, my goal is to take you to the very frontier of this area and see what kinds of observations are possible, what kinds of habitable environments are we talking about, and the diversity of habitable environments that are possible out there, and all the things that we can learn about them. So with that broad brush, I'm Nikku Madhusudhan, as Alexandra gave this kind introduction, and I work on exoplanet atmospheres, and these days focusing on JWST observations of habitable planets. And first off, I would like to thank all my collaborators who are listed here, and more generally, the community, the exoplanet community, for the phenomenal advancements in observations and theory we have seen over the last couple of decades. So I'll start with this question that we have asked as a species for thousands of years. Are we alone? And one could this it's very easy to agree that this is really answering this question is really the holy grail of exoplanetary science. Okay, so we have been asking this question for thousands of years, and it is natural to expect that when we are thinking of life elsewhere and we want to find life elsewhere, the notion we have is one of an Earth twin, an Earth-like planet around a sun-like star um, with life on it, with the planet with habitable planet with life on it. But in order to achieve that reality, if there are planets out there, Earth twins with Earth with life on them, we have two basic questions to ask. Do we have such a planet that is known today? Do we know of an Earth twin? And then, do we have the observational capability to detect a biosignature in such a planet if such a planet does actually exist? Right? So these are two requirements for detecting an Earth-like planet, to have the planet in the first place and to be able to detect a biosignature in such a planet. And as many of you may know, the answer to both those questions is no at present. In other words, currently we don't know of an exact Earth twin, and even if we did, we don't have the observational capability to detect a biosignature in such a planet. Now, there are a number of efforts happening in the field in both those directions, both to detect Earth twins and to detect their biosignatures, and that's a few decade goal. In about 20 years' time, the the expectation is that from the various missions that are being planned right now, and surveys, ground-based surveys as well, we might be able to detect an earth twin and then be able to detect its biosignature. But that's still like in the future. So what do we do now? So fortunately, what has happened in the last a little over a decade is a new frontier is opening up in the search for life. And this lies in between Earth and Neptune in the solar system. So this is, if you look at the solar system, there are the terrestrial planets, Earth and smaller in size. And then there are the ice giants, Neptune and Uranus, and nothing in between. But when you look at exoplanets, what we realize is that the peak in the exoplanet distribution, radius distribution, lies in between those two regimes. Okay, and this is known as the sub-Neptune regime. It has no analog in the solar system, but that's where the dominant planets lie. The majority of the planet population lies currently. So this regime is known as is extremely common, as I just mentioned, but also extremely diverse in all sorts of planet properties. And this is showing an old plot from the Kepler mission, the Kepler planet discoveries, just from the transiting planets. And if you see the sizes, this is the size on the y-axis and the orbital period. So it's a period limited sample. You'll see that there is the Earth and there are the ice giants, as I just mentioned. And most of the planets that from the Kepler mission lie in between those two regimes. And this is just a histogram also saying the same thing, that the peak is in the sub-Neptune regime. And there are a number of facilities after Kepler, the TESS and Cheops mission, which are happening now, and Plato, which is going to launch soon. They're all designed to find more and more of these planets around nearby stars. Okay, so that will allow us to characterize their atmospheres. We already have a few of these sub-Neptune planets around bright stars, but the expectation is that we'll find several more, and also at longer periods if we are going to Plato. So you all know about the transit method. This is just to give a very quick primer. As the planet goes in front of the star, you'll see a dip in the starlight. That is the transit method, basically the transit depth. And then if you have an atmosphere on the planet, some of the starlight is coming through the atmosphere before reaching the observer, the telescope. So this transit depth basically is proportional to the size of the planet over the star squared, basically the area squared, right? So this is just very basics. I'm just running through for completeness. And this is an example. The plot here is of a transmission spectrum of a hot Jupiter observed with the Hubble Space Telescope. This is basically absorption is just the transit depth as a function of wavelength shown on the x-axis here. So for hot Jupiters, we have detected water vapor with the Hubble Space Telescope. This figure is more than a decade old. This is just to make the point that this technique to detect atmospheres of exoplanets is a well-established technique, and dozens of hot Jupiters had been observed already with the Hubble Space Telescope with detections like this, with water vapor detections. So as great as these detections were, there were two limitations. One is the limited wavelength range. You can see that with the Hubble Space Telescope, we could push the wavelength range to a maximum of about 1.7 micron for most objects. And the other limitation was that the sensitivity was such that, I mean, it's a limited aperture, 2.5 roughly meter aperture, which means we could do very good spectroscopy for giant planets, but when you went to smaller and smaller planets, the signal to noise was not so great. So we were limited mostly to giant planets. In just the last few years, what's been happening is that the James Webb Space Telescope is revolutionizing this frontier of atmospheric spectroscopy of exoplanets in general. Why is that? It's because it overcomes both those limitations that I just talked about. First, the wavelength range has now expanded from one to beyond the 1.7 micron limit that we had with the Hubble Space Telescope. So now we can observe, these are some early observations on a hot Jupiter WASP 39b, and we are able to observe in this case, this plot is showing up to 5 micron, but there are other instruments on JWST that can take you almost to 20 micron with varied resolutions across various instruments. So that already, just by the increase in wavelength range, has led to this enormous expansion of the chemical space. So now, because of that expansion, you can see the HST was going just until here, just under 2 micron. But now, because we have longer wavelength range, we are sensitive to a number of these molecules of various elements. So especially water vapor, we had been sensitive before, but now we are sensitive to molecules like carbon dioxide, sulfur dioxide, methane, so on and so forth. And the second major advancement is the obvious one, which is the aperture is more than 2.5 times larger, which means you're that much more sensitive to these features. So now we are able to detect atmospheric features of even smaller planets, not just giant planets, but we are now able to go into the sub-Neptune regime. So both those advancements mean that now we are entering this new regime where with the James Webb Space Telescope, we are beginning to scratch the surface of potentially habitable planets in the sub-Neptune regime. Okay, so this is the outline of the rest of my talk. I'm going to introduce the concept of exoplanet habitability very briefly, and then I'm going to introduce the Haitian paradigm, which is opening up that regime of habitability to temperate sub-Neptune planets in a very special way, which allows us to detect their atmospheric features with the James Webb Space Telescope, and I'll walk you through a case study and some recent results. So classically, you may have heard about the habitable zone. Simply put, it is the distance from a given star over which an Earth-like planet can sustain liquid water on the surface, okay, with an Earth-like atmosphere. So this is just a cartoon, so don't take it too literally. The sizes are not to scale. But this drives home the point that was made already in the early 90s, that if you have a sun-like star, the habitable zone lies somewhere between about 0.97 AU to about 1.7 AU. But if you have smaller stars, the habitable zone closer in naturally, right? Because you can be closer to the star and have the same level of irradiation. But if you go to hotter stars, the habitable zone moves out. So this concept was very well established. Now let's look at the space of these planet sizes and radii and ask how many Earth twins do we know so far? In other words, if we were to focus just on Earth-like planets, Earth-sized planets and Earth temperatures, how many planets do we actually know? So this is a slightly old plot just to give you the sense of the population here. Mostly from transiting planets where you can measure the radii. And if you ask that question, how many Earth-like planets are here, you'll see that it's that box. Okay. So these numbers have increased very recently slightly, but the big picture point is that you have just a handful of planets that are Earth size or smaller and Earth temperature or cooler. Okay, I'm taking 300 as a Kelvin as a rough guide for an average Earth temperature, surface temperature. So you'll see that there are not that many. But now you may ask how many of these are around sun-like stars, and that's 0. I mentioned that point very early on. We have no Earth twins that we know so far. But several of these are around M-dwarf stars. And mainly the TRAPPIST-1 system is what is being looked at a lot right now. And that's because TRAPPIST-1, the star, is a 10th of the sun. So all the planets are much closer in and are still habitable. We'll revisit this in a bit. And we know of several 4 habitable zone planets in the TRAPPIST-1 system, and there's a lot of JWST time that's being spent on that. But that's about it. There are a few more planets which are even harder to observe than TRAPPIST-1 as far as their atmospheres are concerned. So now you see the motivation for going into the sub-Neptune regime, because if now theoretically I could argue that larger planets could be habitable, then I could push this size range to 2 or even larger size planets. And as you go larger and larger, you see many more planets coming in. Okay. So the big picture question here is that what are actually the limits on planet mass, radius, and temperature that allow for habitability? And this is a question we asked about 5 years ago to establish if it is really Earth-size and rocky planets that we need for habitable conditions, or can planets actually be larger and still be habitable and observable as far as their atmospheres are concerned? Okay, so that is where the Haitian paradigm comes in. So this starts with the sub-Neptune K218b. So this was a planet that has been known for a little over a decade now. It was already detected in 2015, and the orbital period is about 30 days, 33 days. And the important thing is that the amount of insolation, the radiation that this planet receives from its host star, is very close to what the Earth receives from the sun. Okay, so this planet, if it were an Earth-sized planet, and Earth-like Earth-like atmosphere, then you would think of it as a habitable planet. But the problem was that the mass of the planet was about 9 times Earth masses and about 2.5 times Earth radii, and basically it is a sub-Neptune, and it has no analog in the solar system. So 5-6 years ago, if you ask someone if such a planet could be habitable, the answer would generally be no, because our notion was that planets that size would have pressures and temperatures from the atmosphere too high at the surface to be habitable. Okay, so these were some of the initial constraints obtained with the Hubble Space Telescope. So this was a spectrum that was detected by Hubble by various studies. And when you do an atmospheric retrieval on it, what we found, and several studies claimed, that there was a water vapor inference. There was only an upper limit for methane. We didn't know it was there, and a strong upper limit for ammonia. But then there was a lot of debate on whether this feature was due to methane and not water vapor, or even star spots. There were some studies arguing that. So when you use the atmospheric composition, there was a degeneracy in atmospheric composition, but the zeroth order inference was that it was an hydrogen-rich atmosphere. And then you can take that information and construct internal structure models of the planet and see what sort of internal structures are allowed. So this is showing radius and mass, and these curves are curves of constant composition. These are known as mass radius curves, as many of you may know. So this curve shows what would be the expected radius for a planet, for a purely iron planet of a certain mass. This is for pure silicate. The blue is for pure water. And then for K218b, if we said what combinations of these various minerals can give us the observed density, the mass and radius within the error bars, we found that there are 3 broad compositions that are allowed. And though I'm listing them here, these are just 3 classes of compositions. The planet, in one sense, could be, in principle, a rocky world with a thick hydrogen atmosphere. Okay, so in other words, a gas dwarf. Or it could be a normal Neptune-like internal structure. So in Neptune, we know that there is a rocky core, and then there could be an interior of a thick mantle of ices, high-pressure ices, and then a thick hydrogen atmosphere. And even for Uranus and Neptune, there is a lot of degeneracy, obviously, if you just take the density information, just the mass and radius. But for K218b, that is also possible, a mini Neptune-like structure. But then there was a third structure which hadn't been thought about before, which we thought was also possible, which was a water world scenario. In other words, the interior comprised mostly of water, but with a thin hydrogen-rich atmosphere. All of those compositions are possible. This was in 2020 that we published. So we agreed with previous expectations for the most part that this planet could not be habitable. Most solutions said that if you look at the pressure and temperature at the boundary between the hydrogen-rich atmosphere and the interior, you would find this is the phase diagram of water in the background, and the red points are the loci of those pressures and temperatures at the boundary. And we find that for most of the solutions, the water is in the supercritical or vapor phase. Okay, so not habitable, not even liquid phase. But we found that for a small number of solutions, the water at the surface is indeed in the liquid phase. So there are a small number of solutions that do allow for a liquid water surface on the planet. And this is another depiction of that, showing that you need a significant, if you have a significant albedo, and that is parameterized here by some enhancement of the Rayleigh scattering, then you can in principle get a liquid water ocean on the surface, but you do need an albedo. If without a proper albedo, this planet, the atmosphere, again, the surface would be too hot and it would fall in this regime. Okay. So there was a lot of debate on this, but the point is, of all these solutions I talked about, the solution of a water world with a liquid water surface was in principle possible. And that's what led us to generalize that concept to a much larger parameter space. So that's what we did in this study in 2021, where we basically scanned the entire parameter space of masses and radii that could allow for similar conditions, the water world sort of conditions. And we found that indeed a large range, a large diversity of planet masses, radii, and temperatures do allow for similar conditions. Now, again, this is not to say that this is absolutely a unique solution. You still have the degeneracy because you only have mass, radius, and temperature information available. But in principle, the solutions of the water surface liquid water scenario are permissible for all these planets in the cyan region. And this is where we came up with the concept of the Haitian world. The word Haitian, as many of you may have heard, is just a combination, a portmanteau of hydrogen and ocean. So this would be planets with entirely ocean-covered surfaces and thin hydrogen-rich atmospheres. So if you were to imagine what such a world would look like, here's the graphical rendition, just an illustration of such a planet, where the concept is one of a planet with no land mass at all, because it's a heavily water dominated atmosphere. We are talking about few to tens of percent of water in the interior. So the surface would be entirely water covered, and then you need enough of a hazy atmosphere to provide the albedo. And then in this case, we are looking at an M dwarf star, as it was for K28b and many of the Haitian candidates. So that's the star in the background. So this notion of Haitian world, suddenly what it has done is that it has suddenly brought the sub-Neptune regime into the dialogue on planetary habitability. Why are we talking? What do I actually mean? What I mean is that if you look at the classical habitable zone and ask how broad can planets be, how broad can the habitable zone be for these sorts of Haitian worlds, you can very easily see that it'll be much, much broader. That's what we demonstrated in the study, is that the habitable zone for the Haitian world is this whole cyan region is much broader than the conventional terrestrial habitable zone. One important factor to note, which had been argued in many previous studies for rocky planets, is that for planets with hydrogen-rich atmospheres, there is basically no outer edge of the habitable zone. You can be very, very far from the star and even have no irradiation and still be habitable. And the reason for that is that hydrogen is not very condensable. It's a very good greenhouse gas, but it doesn't condense until very low temperatures. So you can have a planet very far from the star and still be habitable. Okay. So then there were several chemical studies which also came up shortly thereafter, which showed that if you have a deep hydrogen-rich atmosphere, like a Neptune-like atmosphere, then you expect molecules like ammonia and carbon monoxide, in addition to other molecules like methane and CO2 in the atmosphere. But if you have any kind of surface, in this case, it was a solid surface, but if you have a solid or liquid surface, you can deplete some of these molecules like ammonia. And this was predicted as a signature that one can look for in search of these Haitian worlds, is that if you have a Haitian atmosphere, one way to break Haitian planet, one way to break the degeneracy with other kinds of planet scenarios that I mentioned earlier, is if you see some of these chemical patterns that has been predicted, basically the lack of ammonia or carbon monoxide, that in this case, you can still have a lot of carbon monoxide for specific surface conditions, but it has been shown that the CO2 or CO ratio can be used as a diagnostic for surface conditions, and also the ammonia abundance can be used to a similar effect. Now, again, none of this is set in stone. There's a lot of debate going on, but again, the basic principle to take away from this is that we have uncovered a new class of planets that are potentially habitable, that are in the sub-Neptune regime, that is beyond Earth-like planets. But also, several studies are demonstrating that you can, in principle, use the atmospheric compositions to put constraints on the depth of the atmosphere and hence the habitability of the surface. So then you want to ask, well, what about biosignatures? Can we detect any signs of biological activity on these planets with existing facilities? So we go back to the Earth, and you can ask what are prominent biomarkers for Earth-like planets. And several of you have heard of molecules, of biosignature molecules on Earth to be oxygen, ozone, nitrous oxide, methane, and so on. Methane is not strictly a unique biosignature because some methane can be produced by geological processes here on Earth, but the others are robust biomarkers on Earth. Most of methane is also produced by life here on Earth, so it does qualify to some extent, although not uniquely. So those are prominent biomarkers for the Earth, but are they also good biomarkers for other exoplanets? So generally for Earth's around Sun-like stars, those are being used as good biomarkers, but there is also some debate going on whether oxygen and ozone, even for Earth-like planets, can be produced photochemically in other contexts like M-dwarf stars. But what is also emerging, and this has been going on for the last little over a decade now, is that people have actually almost 2 decades, is that people have identified several other species that are secondary biomarkers on Earth. In other words, those are produced in much smaller quantities by life here on Earth, but are more robust as biomarkers compared to these molecules. In other words, they don't have significant abiotic sources producing them. So there are a number of studies I've listed here that have argued for that. But those secondary biomarkers can become more prominent biomarkers for H2-rich atmospheres because then they become more detectable, even though they could be in smaller quantities. So what are the prospects for detecting biomarkers? So this is showing an example of the TRAPPIST-1 planets. So this is one example where this has been used. A lot of HST and Spitzer time had been used in the past, but more recently JWST has been used to observe the atmospheres of several of the TRAPPIST-1 planets, and we haven't seen any significant spectral features in these systems, in these planets. The reason for that is the inherently low detectability to begin with, but also stellar contamination is a big issue when we are talking about very low mass stars, the very late M dwarfs, which tend to be very active. But when you're talking about Haitian candidates, we had in this study, when we had proposed the Haitian candidates in 2021, we had already shown that with order tenths of hours of JWST time, we can detect multiple biomarkers. in this system, in this planet. So this is showing 3 Haitian candidates from K218b, 270d, and 732c, and we could show that you could detect a number of these normal molecules, methane, ammonia, and so on, if they were present, but you could also detect the secondary biomarkers like DMS and CH3Cl if they were present in the atmosphere. So finally, let me walk you through the recent JWST case study, which many of you have heard results from. So we had a GEO program in JWST cycle 1, where we got about 22 hours of JWST time to look at the planet K218b, the transmission spectrum, with 3 different instruments. And so our goal was not to detect biomarkers. It was to detect these prominent molecules like water vapor, methane, ammonia, along with other trace chemicals like CO and CO2. And the main reason for that is that goal is to detect the possible chemical disequilibrium in the atmosphere. We just wanted to see if the atmosphere is compatible with thermochemical equilibrium, or are there signs of chemical disequilibrium? So this is showing the latest MIRI observations that were published last year, and this is just showing you a white light curve from that observation. So this was the pre-JWST spectrum of K218b, and the first HST is the first JWST spectrum was published a few years ago, looked like this. Okay, so we were able to clearly detect methane features in the atmosphere, along with a very clear signature of carbon dioxide. So I'll come back to the nitty-gritty in a minute, but the bottom plot here is showing you theoretical curves, theoretical contributions from various molecules, just to show where the contributions are. And in addition to robust detections of methane and carbon dioxide, we saw some tentative hints of this molecule DMS, which was predicted to be a potential biomarker when it comes to habitable planets with hydrogen-rich atmospheres, and especially for Haitian worlds from our study in 2021. And you can see now why DMS is so hard to detect is because it has overlaps with the methane band here, okay, with the strong methane bands and the CO2 band. And we do atmospheric retrievals when we have data like this, basically have an observed spectrum and a parametric atmospheric model, and then extract the various parameters, which are the molecular compositions, temperature, and so on. And when you do that, you can see very clear peaks of carbon dioxide in this atmosphere, potential peak of DMS, but then the significance of the peak reduces when you introduce offsets within detectors and so on. But then we don't see molecules like water vapor or ammonia in the atmosphere. And those are also very important constraints for various reasons. So that is the summary, is that we confirm a hydrogen-rich atmosphere, but with high abundances of methane and CO2, and we don't see these other molecules, ammonia and carbon monoxide and water, which were predicted to be good indications of an ocean surface. And we saw marginal evidence for DMS, which was a potential biomarker, and I'll come back to that in a minute. But for the first time, the importance of these observations was that we were able to detect the carbon-bearing molecules in a habitable zone exoplanet for the first time, which was phenomenal. And then, based on this initial chemical predictions, we were also able to argue that a ocean surface provides the best explanation to all the data together because of the lack of ammonia and carbon monoxide in the atmosphere. Okay, so that basically launched a new era in exoplanet science. This was the first temperate planet ever observed, the first sub-Neptune with carbon-based molecular detections, and opened a whole new avenue to study various chemical and physical processes in these atmospheres. But for the next observations, we wanted to see this tentative hint that we got for DMS, whether we can see it in the third observation that we have, which is in the mid-infrared. So if you were to make a prediction, the DMS signature in the mid-infrared would look like this, but there we know that there is another molecule called DMDS, dimethyl disulfide, which has overlapping features with DMS, so there is some degeneracy. But the point is, if we had a MIRI observation with enough signal to noise, we should be able to find these other find signatures of DMS as well. Okay, so then we made this observation. This was the announcement that we made last year, was the first mid-infrared spectrum of K218b and the first spectrum of any sub-Neptune which showed temperate sub-Neptunes which showed any spectral features. So this is what we see. And when we do an atmospheric retrieval, we infer that the feature that we are seeing here could be explained by a combination of either DMS or DMDS or both, but the feature is still at a low significance, as you can tell, right? It was only at a 2 to 3 sigma level. So these are the atmospheric retrievals. So we were seeing peak of DMS or DMS only or DMDS only, or when you include both, the peaks dilute, but that's because of the degeneracy between the two. So we could, based on these retrievals, we could say that it's one or the other or both. So that was a big deal because it was, as I said, the very first transmission spectrum ever detected of a temperate exoplanet, and especially for a planet that we predicted that could be habitable, that's K218b. So this has launched a big debate because for the first time we are claiming that we are seeing independent lines of evidence, first in the near infrared at order less than 2 sigma, and then in the near infrared less than 2 sigma, and then in the mid infrared where it could be the signal could go up to about 3 sigma, depending on your model assumptions. But that is still significant because we had never even expected to be this close to detecting a potential biomarker, right? So that's a big deal. One could argue about the sensitivity, about the significance of the results, but the bigger picture understanding here is that if you want to make a 5 sigma detection, 4 or 5 sigma detection of a biomarker on an exoplanet, your initial observations will pass through those 2-3 sigma results. And that is the important point to note. For example, if you want to detect a biosignature in TRAPPIST-1, you will need tens of transits, order 30 transits or more to detect ozone, which means if you have made only 5 transits or 6 transit observations, you will end up seeing 2 sigma results or 3 sigma results on the path to getting those 4 or 5 sigma results. And I think this is where we are at with K218b. If there is DMS in the atmosphere and if we are to robustly detect it, with one observation, you only expect to see it at a 2 sigma result, if that. So what we are seeing it is actually quite optimistic, much more than what anyone would have expected before the observations. So naturally, there's a lot of debate going on in this topic, and I've listed all the big questions and several works that are happening, both by ourselves and various other teams in the field. You may ask, is the signal authentic? Are we actually seeing a signal? It could be just noise that we are seeing. You could ask, is the signal adequately identified? Is it DMS that we are seeing or something else? And if it is DMS that we are seeing, then are there abiotic, non-biological signals of DMS? And then would life produce such a signal given the environment? And if there are independent lines of evidence? So I obviously won't have time to go through the entirety of the debate, but we'll focus on the main points here. So one thing is clear, both from our and previous studies, that having the amount of DMS in the atmosphere is not a problem. So we are seeing tens of parts per million or higher DMS, and several studies by multiple groups have shown, especially this one is the most recent one, showing that life can actually produce the amount of DMS we are seeing. So that's not a problem. Are there independent lines of evidence? We are seeing similar evidence in multiple instruments, order 2-3 sigma, but both need to increase with time. But then these are questions that are heavily open and being debated right now. Which is the signal authentic, and is it adequately identified? So for the question of what is the signal authentic, what we have done is that we have benchmarked our results against comparable cases of giant exoplanets. So what that means is that we have looked at other exoplanets that are published in the literature. Sorry, there is a typo here. This should be WASP 39b. So there are multiple hot Jupiters for which the same instrument setup, MIRI, JWST MIRI, has been used to look at their transmission spectra. And you can see claims of sulfur dioxide in this case, claims of clouds in this planet, silicate clouds, SiO2 here from that feature. So these are all MIRI observations and all at a similar level of significance. We are talking about 2 to 3 sigma significances with very similar retrieval architectures, similar number of molecules, and so on. So the question about whether this signal is authentic is pegged at a similar level to all the observations of comparable with the same instrument for hot Jupiters, even with the same at comparable signal to noise. Okay, so we want to ask. So the answer to this question is that the signal is only as authentic as various other signals that have been published before for hot Jupiters. Okay, so that's the benchmarking that's going on. In an absolute sense, one could argue that none of these results are significant, which is fine. But then if we want to claim any of these results, previous results are significant, then we would have to contend with the fact that we probably are seeing a significant result here as well. Okay. So that's the benchmarking that's happening. And then you could ask, is the signal uniquely identified? So there was a study immediately after ours which argued that the same spectrum that we are claiming DMS with could be explained with another molecule, in this case propine, or 5 other molecules. So 6 molecules from a large search of about 90 molecules. But most of these molecules are anthropogenic in nature. They're petroleum byproducts or other complex hydrocarbons for which there are no abiotic sources currently known. But the point is to be made that maybe our search space, we have looked at only 20 molecules initially, so maybe that search space is very limited. We ought to be looking at more molecules. So we did that. So most recently, this paper is just being published this week, but it's been on the archive for a while, which is instead of going from 20, so previous study had gone from 20 to 90 molecules. What we said is that let's take every single molecule out there for which there is a cross-section available and search for all of those molecules in the data and across all the data that's available, the mid-infrared as well as near-infrared. So we could find, initially we could find only 3 molecules that are promising across all the data that we have, and one of them is DMS. Okay, so and the other 2 also don't have significant abiotic sources. So the bigger picture point here is that we are either seeing DMS in this data at low significance, or we are seeing some other complex molecule that also doesn't have an abiotic source. So then another study argued that this is all, it could be systematics, but then even they found that even if you play around with different data reductions in different ways, you are either seeing peaks due to DMS or DMDS, or another molecule, in this case, it's chloroethane, which is also a complex molecule with no abiotic source. Okay. So finally, there is more data coming especially in the near infrared. There is this recent paper which is on the archive that one can look at. And what we are finding is that we are confirming previous detections of methane and CO2 in the atmosphere. So the CO2 was questioned by another study, Schmidt et al. Last year, but now with more data, we can robustly say that we are detecting CO2. But the DMS, we still are only in the 2 to 3 sigma regime, even with more data. But the important thing is that the evidence has increased, because previously with the same configuration in the near infrared, we were finding less than 2 sigma in the best case scenario, and less than 1 sigma if you had all the offsets, 2 offsets in the detectors. But with the new data, with the maximal number of offsets, our significance has increased to between 2 to 3 sigma, which is great. So we will see if all these hold up. We are still in the low signal to noise regime. As I said, there is a lot of debate underway. But the exciting thing is that we are beginning to see evidence for complex excess absorption in these atmospheres, which may or may not be due to life, but there is promise. So finally, I'll end with my future outlook. As I said, there are a number of open questions on the inference of DMS itself, but there are also a number of theoretical questions people are working on. Is a liquid surface ocean actually possible? What sort of albedo do you need? There's a lot of debate and activity happening in each of these domains. Is a deep H2 rich atmosphere possible with no ammonia? What are the robust indicators of life? How common are Haitian words, and so on. So I'll leave you with these big picture questions. I'll just focus on just a couple of them to tell you about what's coming. One big question is, did we just get lucky with K218b? Right? So it was the first temperate subneptune for which any carbon-based molecule had been detected. So that was a big breakthrough. But did we just get lucky with one target? Turns out the answer is no, because soon after, just last year, in the last 2 years, there was another planet, TOI 270d, which was also a candidate Haitian world and a temperate subneptune that had been observed with JWST, and we, as well as others, are seeing significant features. Look at the similarity between the two spectra. We're seeing significant features of methane and carbon dioxide in that as well. And then we are seeing an additional feature due to CS2 and as well as excess absorption in this range, which could be DMS or could be something else. Then did we get lucky twice is the question. So if you remember our 2021 paper, we made predictions for 3 different planets, subneptunes as candidate Haitian worlds. Now we have data for all 3 of those planets. And there you go. Now you just have to look at this data and take a moment to realize how important a time we are living through right now. For the first time in history, we have not just made the first detections just 3 years ago, but already right now we have similar data for 3 different planets. And in all cases, we are seeing robust detections of methane. In some cases, in 2 of the 3 cases, we are seeing carbon dioxide. But in all cases, we are seeing evidence for excess absorption beyond just methane and carbon dioxide. So in this third planet, we are seeing excess absorption, which could be due to several different molecules. And one of them is DMS, but it could also be several other molecules, all of which are complex hydrocarbons. So the work is still progressing, still on that. So the bigger picture point in all of this is that we are for the first time seeing new insights into an exotic planetary regime. We are either seeing some new chemistry that has no analog in the solar system, and because all of these complex molecules we haven't detected in any hydrogen-rich atmosphere in the solar system, or there is a chance that we are actually seeing evidence of biology. We are not claiming that that is what we are seeing for sure, but we cannot rule that out either. And that's the major development that's happening. And so that's the atmospheric signatures we are talking about. But now if you think about these Haitian worlds, you can ask, what exactly do these planets look like? Then a simple calculation will tell you that you have a hydrogen-rich atmosphere, and if you ask how deep is the Earth's ocean, it's about 10 kilometers deep. But if you have a Haitian world with a lot of water, the ocean basically never ends, in the sense that you go very deep. You can be hundreds of kilometers deep and just have liquid water ocean, and then the water turns into high pressure ice at the bottom. So you don't have a rocky solid floor, it's just water as the floor of the ocean. So these are kind of the exotic planets we are talking about. So I'll end by saying we have made 3 fundamental advancements in the search for planetary habitability, in the sense that we are making probably the first contact with potential habitability. We don't know if these planets are definitely habitable, but there is the potential. And I've demonstrated that we have now gone far from literally Earth-like planets to planets that are much more exotic and have the potential for habitability, regardless of whether what we are seeing is a biosignature or not. And then we are seeing a unique congruence of a theoretical prediction and observations confirming those predictions. And then we are uncovering a new class of temperate subneptunes with a lot of exotic phenomena that we will be uncovering in the time to come. And the promise of this decade is that it literally serves as the launch pad in the search for life, because we have the targets, as we have just demonstrated, and we have the facilities. The James Webb Space Telescope is happening now, and you've seen some great data from that, and then the ELT will be coming very soon. So we are in a new era in the search for habitable conditions and life elsewhere. Thank you.
Thank you very much for it was very interesting presentation. I would like to ask the listeners, do any of you have any questions? You can raise your hand or write in the chat. So it seems okay. Um, if there's no question from the audience, I would like to ask a question. Among the recent James Webb Space Telescope observations of light candidate
So there
Heisenbergs.
was, sorry,
Hmm?
Alexander, there was a question by Daniela.
Okay, yeah. I see.
Question is, can I comment on abiotic sources of, I suppose you mean DMS?
Yes.
Yes. Okay. Yeah. Thanks for the nice question. Yeah. So for the last 20 years, people had predicted DMS as a robust biosignature for both for Earth-like planets as well as hydrogen-rich atmospheres and so on. But recently, there has been quite some debate on potential abiotic sources. So there is an argument that if you have a deep hydrogen-rich atmosphere with enough H2S in the atmosphere, then the combination of H2S and CH4 can in principle give DMS. So there is that argument being made. But for that argument to work, you need a lot of H2S, which we are not seeing. And you also need a deep atmosphere, which is we are not seeing. I mean, the lack of ammonia is arguing against the deep atmosphere scenario, but that could be a viable mechanism that people are looking at. And the other argument people are making is one of comets. So people are saying that DMS, there was an inference of DMS. I think it was also a 2 to 3 sigma inference of DMS in Comet 67P. So they're using that to say that maybe there are other ways to make DMS because it was made on a comet. To me, that is a slightly weaker argument because the same comet also has molecular oxygen in it and methane and all sorts of. There are lots of molecules that we can make on comets because complex chemistry is very easy to happen on comets. But in an atmosphere, those molecules are not very stable. And for the same reason, why O2 is a very good biosignature for Earth-like planets, even if you can find them on comets, right? So that to me is a slightly weaker argument. There is also people have said there was one paper which says they found DMS in the interstellar medium, and it's the same argument. So to me, that's a slightly weaker argument, but the point is that the point of making it in the atmosphere itself with enough H2S is a good one. We'll have to see if that holds for this particular planet. CH3SH is a good one. There was one I showed you briefly. Let me pull up that slide. Where we think we are seeing evidence for that in more recent data for CH. Mercaptan is what you're saying, CH3SH. I'll show you this. Yeah, so this one. So we think if you see here in these posteriors, so there is a degeneracy between DMS, methyl mercaptan, and N2O. So if you use any one of those molecules in the retrieval, we are picking up mercaptan. But when you look for both DMS and mercaptan together, the peaks sort of dilute. The posteriors are diluted because there is common features between those two molecules. So there is a degeneracy. So that's an exciting question, actually. Not many people pick up on that, but that's an important subtlety, is that in principle, we may not be seeing DMS, but we may be seeing some other biomarker like CH3SH.
Thank you. Um,
Alexander, you had a question?
yeah, I also had a
Thank you.
question. You mentioned the 3 planets, for example, the K2-18b, like that are possible Hessian worlds. Are there other like new planets coming up with the new observations? Or are
Yeah, there are at least a couple more where there is data available with JWST. But I would say these would be our best targets because we had predicted, this is why we predicted in our study, because the signal to noise, you can tell the stars are brighter, the planets are on the larger end. So we knew upfront that the signal to noise would be the best for these 3 planets. So we went for those first. But there are also a couple more planets that are coming, which are at lower signal to noise. So exciting times overall. We would have about 5 to 6 planets to look at. As a field, we would have order 5 to 6 planets we can study. And these may not end up being Hessian worlds, but they're still extremely interesting because you have data. So you can do lots of chemical characterization and constrain various processes.
yeah, but that's true. I was thinking maybe like the black door area emission can also like help widen the, at least part of widen the like selection of maybe there are more planets, and then Ariel can maybe help with the calculation of the atmosphere. So that would also
Absolutely.
interesting case. Yeah.
Absolutely. So there is a lot to look forward to with Plato and all the new efforts that are happening. There's a lot to look forward to in the characterization because, if you go 10 years ago, we had no sub-Neptune detection, atmospheric detection, right? They were all flat spectra for a long time and everyone was frustrated. But for the first time, we are seeing features. You can argue about the interpretations, but we have data, we are seeing clear features right in front of you. And we have several of these planets, not just one, right? So which means it's looking very promising where as we make more and more detections and cooler planets, we kind of now know what to expect, or at least as a starting point. And then this basically opens up like that whole area, and it's very exciting.
Yeah. I don't know, does anybody else have a question? Yeah, I think maybe not, but thank you very much for coming and giving us a seminar. It was very interesting. Hasian worlds. I have also heard about them before and read about them, and it has been cool to get to know more about them from you.
No, thanks for inviting me. It was a pleasure speaking here.